This is where we left off last time. I'm going to sketch again the idea here of having our planet and a first spacecraft, which we call the chief satellite or target satellite. There's a lot of different names that you can find in the literature, but that would be your reference satellite. And so its position is given by the vector RD, and RC, this is the chief. And the LVLH associated with this has the x pointing in the radial direction. The z-axis is normal to the orbital plane. And the y-axis is the cross product of the two in general. Bless you. So this satellite for now is on a generic orbit, whatever that is, no assumptions. We do make the assumption that we only have Keplerian motion only to derive those differential equations I played with at the beginning of last lecture. There are more elaborate models that try to include the J2 effect in the equations of relative motion, but that's definitely beyond the scope of this class. So we assume that basically the two satellites that are involved only see a force mu over r cubed r. And then we have a deputy satellite here, whose position vector is of course called RD. All right, so it goes from center of the planet to the satellite itself, and we would like to, this is the vector that connects the two, we would like to linearize the motion of the deputy with respect to the chief, which is the point of linearization, using this kind of coordinates in LVLH, okay? So this basis here is the LVLH, local vertical, local horizontal. Of course, the chief is moving. Point of linearization doesn't mean that you're looking at some state that never changes in time. That point is moving in the inertial frame. But since I'm using those coordinates, my point of linearization, if you want to put it in a state space form, it is the vector x naught, y naught, z naught, etc., where I choose them to be what? If the chief is the center of that coordinate system, this is what I'm choosing, right? So in all the symbolic calculations I worked on at the end of last lecture when I talked about linearization of a nonlinear system in general, where you compute the A0 and the B0 matrix using the Jacobians, you do your calculations for the Jacobians, and then where you see the state, you plug in this case, a bunch of zeros, because that is my reference point. And the chief is sitting at 0, 0, 0, with zero relative velocity with respect to itself in that LVLH basis. Does it make sense? Yes? No? Okay, so that is my point of linearization. And so, since I'm looking at this guy and I want to see how it's moving with respect to the chief, hopefully not too far away, so I want to linearize, I started from this equation, which is pretty obvious. The position of the deputy is the position of the chief plus del rho vector that connects the two, which in the basis that I'm using can be projected as RC plus X I. So I know I'm confusing X hat with I hat. I mean, I just don't want to use X because I'm using it here. So if you want, remember this is the X direction, this is the Z direction, unit vector is K, and this is the J. We only really have that coordinate system that we're using right now. So there's no room for confusion, hopefully. Plus Y, J, and Z, K. Is this step clear? I am projecting the deputy's position vector in LVLH. The I direction of LVLH is, by definition, is R chief over its norm, right? Remember this? So that's why I can do this. RC itself only projects in the I direction. There's nothing else. Okay? All right. Well, I'm talking about equations of motion, so I need to get to the second time derivative of that position vector. The first one, RD dot, I think that's where we left off. I can, using the transport theorem, express it as the rate of change of the RD vector with respect to LVLH plus the angular velocity of LVLH with respect to ECI crossing RD itself. So obviously somewhere here there will be an observer that is still using the ECI that we have defined at some point, right? Big X, big Y, big Z, where the x-axis is pointing as the line of the vernal equinox. That's Z. Sorry. Z is the spin axis of the planet, and then you cross the 2. That's there. But RD dot, as we have agreed at the very beginning of the semester, when I put a dot on top of a vector, I mean the rate of change of that vector with respect to the inertial observer, right? Remember? So for me, writing that or this is the same story. So that's just the transport theorem. Okay. So let's figure out what these pieces are. What is this one? Time derivative of position vector RD with respect to ECI. With respect to LVLH. These guys are not changing in LVLH, right? So I look at this vector, which is RD. I take time derivatives on everything except these 3 because they don't change in LVLH. And so I have RC dot plus X dot I plus Y dot J plus Z dot K plus what is the angular velocity of LVLH in ECI? Please note that I have started using the LVLH basis. I have expressed RD in this basis. I am taking its rate of change in that basis. So how about I stick to that basis? So can you express this angular velocity of LVLH frame with respect to ECI frame in LVLH? What is happening to the chief if it is moving on a purely Keplerian orbit? If this is your ECI, this is your line of nodes, this is your orbit, generic orbit, okay? This is your angular momentum vector, H. The plane of the orbit is not changing if it's purely Keplerian, meaning that RC double dot is nothing else than minus mu RC cubed RC, okay? And the same would happen for the deputy if both they only see a perfectly spherical planet. That's all you have. So this will apply to both of them unless you maneuver. The plane doesn't change, right? Go back to your GVE's equations. If you don't have perturbations, they don't change. Big omega inclination, little omega don't change. Same with your axis, there's no reason for that to change. Eccentricity doesn't change. So in particular, at any particular point on the orbit where your chief satellite, in this case, may be, this is going to be your I direction. Bless you. The Z or the K unit vector direction is parallel to H, and then you cross the 2 and you get the other one. I, J, and K. That's how I call them. Is K changing over time? It's not changing, right? All this basis is doing is rotating with an angle. Say that this is the direction of the, so this is line of nodes, this is your line of ops. Remember, it's the direction of the eccentricity vector. So from this line, you measure position with the true anomaly, theta. So the only thing that is really happening is that this basis is rotating about the H vector or K vector with an angle theta. That's all it's doing, right? the fact that the I and j unit vectors are not sitting on the equatorial plane, it's irrelevant. It is just a single axis rotation about the k direction. Do we see that? Okay, so I'm going to ask you again, what is this? How do I write this in light of these observations projected in this basis, I, j, and k? Theta dot k. Yeah, that's all. Right? And now this is crossing. I can't fit it in here, but it's crossing. What is it crossing? Well, RD again, right? So that entire vector, should probably take a little more space here. RC plus x, I plus yj plus zk. Okay. All right. Let's do it. The first part remains as it is. RC dot plus x dot, I plus y dot, j plus z dot k plus little refresher on kinematics, right? What is the first one? Of course, the last one I'm not going to bother doing this, right? K cross with k is 0, so I just care about these two guys. Okay, what is the first one? I'm gonna start writing stuff down here. Theta dot RC plus x, that's for sure. Those are the scalar parts of this cross product, right? Then I have to care about k cross with I. What is that? Is it j plus, minus? All right. And then this vector, theta dot k with yj is minus theta dot y. Which direction? All right. So collect all these together. This is what you get on the three directions. RC dot plus x dot minus theta dot y on I plus, in the other direction you have y dot plus RC theta dot plus theta dot x j. Is that right? Think so? And then finally you have z, I need a parenthesis on this one, z dot k. So remember, all this is doing is first time derivative of the position vector of the deputy with respect to ECI. I have to do the second one. So RD double dot, which I know by assumption that I only have a Keplerian force, is this. I know this, I'm assuming this, right? Well, it is also equal to, same story, the rate of change now of RD dot with respect to LV, LH plus angular velocity of LV, LH with respect to ECI, which is crossing with RD dot. And I don't know if I want to do all the steps, which I have in my notes, because it's pretty tedious. There's nothing special about this. It's doing that with more vectors. So we can start, and then I'll give you what it looks like, and then we'll make some assumptions, because that's the point where we can make some assumptions for the Cloyce-Wilshire equations that we'll derive. Well, the first one is you take this vector and you start looking again at the scalar parts only. So you have RC double dot plus x double dot minus theta double dot y minus theta dot y dot. Bless you. Wow. I plus, same with the second component, y double dot plus RC dot theta dot. This is a product. Plus RC theta double dot. Plus, let's see, theta double dot x plus theta dot x dot on j plus, that's an easy one. z double dot k. And then I have to cross same vector I had there, theta dot k, which is the angular velocity of that basis that is moving with the chief with respect to ECI, with this entire vector down here. All right? Theta dot y, I plus y dot plus rc theta dot plus theta dot x j plus z dot k. So that's what you have to do. Now if you go through those few cross products here that really matter, these two, when you reorganize as appropriate in the three directions, this is what you get. Let's try to make it fit in here. Let's see. Verify it if you don't believe me. It's really just a couple more steps. Okay, minus 2 theta dot y dot minus theta dot squared rc plus x. I, on the second direction, I have something as long as this, y double dot plus 2 theta dot x dot plus rc dot minus theta dot squared y plus theta double dot rc plus x on the j direction, and then the most beautiful one is the last one, z double dot k. Done. Now this is your acceleration of the deputy in ECI, right? This is the final result for now, which again I also know it's equal to this, because this is my force model, okay? This is my gravitational field model that I have. So these two things are the same. This clear? Now, the equations I gave you at the very beginning of last class, as I said, I don't know if I wrote these, are called Cloyce, Wiltshire, those linear equations, or Hill's equations, because they were developed in parallel by different people. They make some assumption on that equation where all this expression here is equal to minus mu over rd cubed rd. Linearization is one of them, and we have to do that yet. But the first one is, first assumption, chief is in a circular orbit This is extremely relevant for rendezvous and docking with the International Space Station. If you look at the time history of eccentricity for the ISS, it barely exceeds, I think, 0.04 right after a maneuver to regain altitude. It really stays circular at all times, pretty much. So it's a very reasonable assumption for many applications, and that's how we get those equations I gave you. So if the chief is in circular orbit, there's a lot of stuff that goes away there. Which of those time derivatives I can throw away? Yes, so if the chief is in circular orbit, this means a series of things. The norm of the position vector of the chief is constant, right? So RC dot, and as a consequence, RC double dot, they're zero. Agree? Chief is moving on its orbit, the vector is changing, but the norm of the vector is not. And that RC that you see there and RC dot, those are norms, right? Agree? Okay. There's also theta double dot, which is zero, because the theta dot, the angular velocity of LVLH, is what we called at some point the mean motion, and it's a constant. You can call it omega. That's I think how I actually called it in the equations I gave you last time, or just called it omega. It's a constant. That basis, LVLH, is rotating about the k-axis at a constant rate, because it's always attached to a circle, right? Okay, so there's a lot of stuff that goes away. If you substitute theta dot with omega there, remove everything that has a theta double dot or an RC dot or RC double dot, we have that RD double dot looks a little nicer. It's going to be x double dot minus 2 omega y dot minus omega squared RC plus x in the I direction. Then we have y double dot plus 2 omega x dot minus omega squared y in the I direction, and then finally the z double dot. We want to stare at this for a minute. I do have the I direction twice. Today I can't just get that right. Thank you. Okay. Well, no brainer with z double dot. That doesn't change. Let's go here. Y double dot, I keep that. Of this product, the RC dot goes to 0. I call theta dot omega, so that is my 2 omega dot x dot, 2 omega x dot. Theta dot squared y becomes this term here, and then, right? And then this goes to 0 because it's theta double dot, so that's fine. The first term, RC double dot, goes away. X double dot is there. Minus, no, this goes to 0. It's a theta double dot. Minus 2 omega y dot is right there. And then I have this, which becomes an omega squared RC plus x. So it makes sense. Okay? Well, I do know, as I said right there, that this is equal to minus mu RD cubed RD. Let's express these also in the same basis, which is pretty easy to do, right? It's minus mu RD cubed. Let's express these as IJK. How do you do that? Well, the same I've done before. It's RC plus rho. So this is multiplying RC plus x, I direction, plus y, j. Got this right this time. ZK. All right. Agree? I don't like it this way. Let's put it as a system so that this starts looking familiar to what we saw last time. So on the x direction of LVLH, this is what I see. This is the left-hand side. And on the right-hand side, I have minus mu RD cubed RC plus x. The second equation is y double dot plus 2 omega x dot minus omega squared y, which is equal to the same coefficient here, RD cubed y. And finally, z double dot is minus mu over RD cubed z. Agree? I've just taken that vector equation, I just wrote it down component by component. I don't want the I, j, and k fly around. Okay. So that was achieved in circular orbit. To get those equations, this starts looking familiar, right? The second one is linearized. Those equations, again, these equations right here, they are linearized equations for how the deputy moves with respect to a circular sheaf. Okay? So what do I have to do with these equations now? Any ideas? Nope.
Rearrange them so that you have all the double time derivatives on the left-hand side?
Yeah, but there's no double time derivatives. Well, yeah, eventually I can do that. But these I want to get them in the form that I gave you last time, where this wasn't there. There was no RC, if you recall. You can get to that form from here. But the main question I have, are these linear equations? Right, they're not. What is RD? RD is the square root of RC plus X squared plus Y squared plus Z squared. Do we agree with that? So I don't like this thing down here to begin with. Just by itself, even if it wasn't a denominator cubed, just by itself, that element right there is not linear, right? The square of x, the square of y, square of z, there's a square root, there's all sorts of stuff going on here. So I need to linearize those equations. I need to make that non-linear term disappear. Okay, let's do it. Let's get rid of it. So we'll start with this, exactly with this one. Let's rewrite it like this. This is equivalent to x squared plus rc squared plus twice rcx plus y squared plus z squared. Now I like this additional expression here. Take the rc out. At this point this is a constant, okay? I assume the chief is in circular orbit, so radius of the chief circular orbit is a constant. 1 plus 2 x over rc plus x squared plus y squared plus z squared over rc squared. That's equivalent. I just taken rc out. So let's look at this one, this first non-linear term. They're all non-linear, but I'll just do this one, and the other ones they just follow with the same procedure. So let's linearize. Let's linearize that first term. That first term, except the minus mu, that is a constant, I'm just going to basically focus on rc plus x over this entire thing here, cubed. So that means rc cubed multiplies 1 plus 2x over rc plus x squared plus y squared plus z squared over rc squared, everything to the 3 over 2. Agree? So that is my f, if you want f1 of x. Remember what we said last time? You have a nonlinear system, you have f1, f2, f3, you have different nonlinear functions. So we want to linearize that. Okay. And f, so first thing is f in x0. What is f in x0? Remember, x0 is a bunch of zeros. My point of linearization is the chief, where all those coordinates goes to 0. Here there's not even x dot, y dot, z dot, so everything is just a function of x, y, and z. So if I plug in 0, 0, 0, 0 everywhere, this becomes 1 over rc squared. That's it. So this goes away, all this stuff goes away. You're just left with a 1 here, so it's 1 over rc squared. Okay. We'll keep that in mind. Then I don't think no, I need this. I don't need this anymore. Then I need to take partials, right? Okay. So this one, how do you do this? Do you remember? Denominator times the derivative of numerator minus numerator times the derivative of the denominator over denominator squared. So it's ugly, but everything that goes in here in my next calculation will appear like 3 dots. How about that? I'm not going to write that all over the place. So this is what I have. I have rc cubed times that 3 dots to the 3 over 2 Okay? Then what? What does that multiply? That's denominator as it is times the derivative of the numerator with respect to x. So that stays as it is. Minus, now I take this monster here and I take its derivative, so everything that is below there under the fraction, I have to do the derivative, so it's minus 3 over 2 RC cubed. Now this becomes whatever is in there to the 1 over 2. Okay? Agree? That multiplies. Well, I'm not done. Am I done? Yeah, I was going to write RC plus X. But I have the notes defending me from those mistakes. I'm not done. I have to take the derivative of what's inside with respect to X. I have 2 over RC, right? That is this piece here with respect to X. And then this other one here. That becomes 2x over RC squared. I think that's it. Now I can multiply times RC plus X. We're almost done. And down here you just write your denominator squared, which is now an RC to the 6th power, and whatever is in that parenthesis to the 3rd power, and that's it. Okay. Whoa. Now, if I take these and I plug in a bunch of zeros, wherever I see x, y, and z, what do we get? If you plug in x, y, and x, y, and z equals to 0 in that parenthesis, you're just left with a 1, right? So here I'm left with a 1. So I have an RC cubed. Let's see, a minus 3 over 2 RC cubed. This becomes a 1. Down here I'm only left with 2 over RC, right? You see that? Because this is 0. And here I'm left with RC. Alright, there's a lot of RCs flying around. And then RC to the 6th power, this becomes a 1, so that's gone. And so you simplify a few things around here. The 2 goes away, this goes away. Bless you again. You have RC cubed minus 3 times RC cubed over RC to the 6th, which is minus 2 over radius of the sheaf cubed. So my f of x becomes, what does it become? Remember the expansion we looked at last time? So, 1 over RC squared, why? What do you think? What would you do? Remember, what am I linearizing? RC plus X, all this term, right? What do you want to do? Except the minus mu. We can put the minus mu there at any time. Ideas? No ideas? I have these. This is my term here that multiplies x. This is just another way of rewriting that, just because it's convenient for me for the next step. So this is just rewriting f, what did I call it there? F in x0, right? 1 over RC squared. I just multiply top and bottom with an additional RC. So this is f, the function at the point of linearization, plus the derivative of the function times x. Agree? Okay. So collect that. You have minus 1 over RC cubed that multiplies RC minus 2x. The same way you get the other derivatives. You can prove it to yourself. But let's substitute these in those equations. I don't know if I want to erase this. I'm going to rewrite it here. So, if that is my approximation of this one, I have x double dot minus 2 omega y dot minus omega squared RC plus x. Okay, this becomes, remember that I had a minus mu, something about the signs here.
I don't think there should be negative signs.
Right, that's an additional one that I don't like. Thank you. Yep, it's not there. Now this makes sense, because I have a minus mu over RC cubed, RC minus 2x for this one, right? I have linearized that right-hand side that was non-linear. Now there's nothing that is non-linear here anymore. This is a constant, this is a constant. It can stay down there cubed, I don't care anymore. It's not little x, little y, or little z. Omega is a constant, everything is a constant in this equation. Except the x variable, and the y, and the z. But the rest, they have to be constants. And they have to be in non-linear expressions. All the x, y, and z, which they are. I don't see anything wrong anymore. Y double dot plus 2 omega x dot minus omega squared y. Now you can prove to yourself with the same procedure that these are linearized, the second one linearized becomes minus mu over RC cubed, just y. And finally, last one, it's always the nicest one, is minus mu over RC cubed z. Okay? Does this remind you, this thing, of anything? What is the circular velocity on an orbit? The velocity of a circular orbit, what is that? Mu over r, right? If c is its radius. Is that right? What is this? Has something to do with that. It's omega squared. Believe it or not, that's what it is. You can double check. It's a circular orbit. There's nothing special about it. So take that velocity and write it as omega r, and extract the omega and square it. That's what you get. So if all those things become omegas, then I have my final equations. I have x double dot, so not just that one, okay? This one, this one, this one, except the minus, they become other omega squares like this one. So this term, for example, becomes a minus omega squared RC. I have the same one here, that goes away. Then I have a 2 omega squared x that moved here, becomes another minus 2, so this will become a minus 3 omega squared, and so on and so forth. At the end of the day, you get exactly the equations we started from last time. All right? These are your Cloyce-Wilshire equations. Or often called CW equations. the most famous and oldest equations for spacecraft relative motion. GNC of space shuttle would be based on this when approaching the ISS. They're the linear time invariant equations. This is where we started from last time, and now this is going back to the comment. You move all the second time derivatives to one side and do the little trick we did last time. So these are obviously expressible also in this form, right? And you may have here, we'll have to talk about that, you may have some inputs, thrust inputs. And we need to understand how the thrust in ECI maps into LVLH. We'll get there, but in principle, there may be some other stuff there that represents control actions, engines, whatever it is, drag forces. But for now, there's nothing else than Keplerian motion. The two objects are relatively close to each other. We'll see with some simulations how close they can be until these equations break down, because these equations do break down. If your satellites are, chief and deputy, 1,000 kilometers away from each other, these equations, forget about using them. They're not going to approximate reality very well. But if they are a few kilometers away from each other and below, they are reasonable. Okay? Definitely your chief has to be in circular orbit. There's a lot of assumptions here. Chief has to be in circular orbit. They don't need to be super far away from each other, but if those are respected, these simple equations give you a lot of insight because they are linear. So we'll probably see something in MATLAB if we have time, but before we do that, what are the things that you have seen over the years that you can do with linear equations? You can use Laplace transforms, you can do with systems as well, right? So you can characterize the time response of these equations. By the way, notice that this one down here, the Z1, is completely independent from the other two. It's an harmonic oscillator, that's all it is. X double dot plus omega squared x. There's just a Z there, but it's an oscillation, right? Sinusoidal wave. This is a constant. So, in fact, the Z motion in this version of the relative, this linearized world that we're living in right now, the out-of-plane motion, how the two satellites move with respect to each other in the Z direction of LVLH, is completely disconnected from the in-plane motion. So this is the out-of-plane motion. We call it out-of-plane, the Z1, while these two guys here represent the in-plane motion, where we mean XY plane of LVLH. These two are coupled. You cannot solve the Z1, you can solve it by yourself. These two are coupled. You cannot solve the Y motion without solving the X and vice versa. They go together. But the really beautiful thing about linear equations is that you can solve them analytically. In other words, if I gave you initial conditions, x0, something is going on next Monday, that's all I got. So if I give you some, and now 0 here doesn't represent point of linearization, I'm sorry, I know this is maybe confusing, but I give you some initial conditions for these differential equations in relative position x, y, z, and relative velocity x dot, y dot, and z dot in LVLH, okay? This is how the deputy at time 0 is moving with respect to the chief. Its position with respect to the chief at some given time in LVLH. So say that this is LVLH I, j, and k. Your chief satellite is sitting always down here, and this is just the rho at some initial time and its time derivative in this basis. So these are the deputy. So say that I give you this. You don't have to integrate these equations numerically as we've done for many different equations. The Keplerian motion plus J2, the Gauss variational equations, you should have done all of that, right? In your uncollected homeworks, etc., etc. You don't need to necessarily go and use OD45 for this. In other words, if I give you that, so given an initial state, let's call it big X0. So given X0 and T, you can just analytically tell me what is X at that given time. I know my position and velocity in LVLH at time 0. I want to know the x, y, z, and their time derivatives in 100 seconds, whatever it is that you're looking at, you can just have that solved analytically without integrating them. Yes?
When we linearize the first equation, we only take the partial with respect to x.
Mm-hmm.
Instead of the other two variables.
Try it. See what happens. Yep. Yep, that's a. I was waiting for that question. Try and see what happens. It goes to 0. Yeah, they should. Yeah, that's a good point. So, as I said, try to finish this linearization here. I have done, as he said correctly, I have done the partial with respect to x. Do the other ones and see. So, do follow the procedure that I outlined in general last time without looking at any particular system. Well, I think we did have an example, right? But basically what happens is you do the partial of f with respect to y and partial of f with respect to z for the first one, whatever it was before, the nonlinear version. Do those, plug in, there is a linearization point, and they should just go away. Okay? But the procedure is what we've done. Okay, yeah, we have a few minutes. Do you agree that if you have a system of linear time invariant differential equations, you can do it analytically? No? Okay, so does this look familiar? Let's see, e to the a t x 0, where the exponential of a matrix times t is this infinite series here, k that goes from 0 to infinite, 1 over factorial k at to the kth power, where k equals 0 is basically implying that you have the identity matrix. Does this look familiar? This is x of t. So this is actually satisfying my system, right? X of t is indeed equals to axt. So if I'm claiming that the analytical solution for a system of equations like this can be expressed in this form, where this is an exponential of a matrix, and that is something you should have seen in some other classes. This is k factorial, by the way. Okay, factorial k. If I claim that this is a possible solution where this is my initial condition that I gave you, and this is the exponential of at, where a is the matrix that we have derived last time, when I started from these equations, well, I can prove that that is a possible solution because I take its time derivative, this is how it looks like, and this is again x of t, and so this is satisfying my way of writing LTI equations, right? You don't remember these from any classes? You should, right? So these equations do have a solution that can be expressed that way. That can be done in MATLAB, of course. We're not going to look into any particular techniques to express, to compute this exponential. MATLAB actually can do it for you if you give it the 8 matrix, and that's all we're going to do, probably next time at this point. But this is extremely useful. To have analytical solutions for dynamics means that, for example, if I look at the problem in a different way, I am giving you an initial condition, right? Like in this case. And I'm giving you a time. And not only I want to know where I'm going to be, I want to control that. So at time t, I want this to be, for example, a bunch of zeros. I can tell you what is the delta v, the maneuver I need to apply here to drive my state to go where I want it in 100 seconds. Does that make sense? If you have analytical solutions, the mapping between a certain time and another time, there's no numerical integration required in between. You can play with functions, with closed form functions. So we are definitely going to start seeing that next time. We'll do this in MATLAB. I'll show you what the analytical solution looks like, make a few comments on that, and then we'll look at two impulse maneuvers for relative motion, how you can go from an initial position to a final position with two burns. Okay, thank you.